So we had seen in the last class about blanking and piercing, right? And we had seen how that clearance is important and how that clearance is kept, right? And the different allowances that we keep. And yes, as for the punch and die, because this is the most common combination that we have, isn't it? For blanking and piercing, that's what is required. The basic tooling, die and punch. So, and how that angular clearance is also kept. If not kept, then we'll have that damage of the workpiece, right? Both the workpiece and the die surface as well. So let us have a look at video and animation so that we can understand blanking. Yes. Let us have a look at this process, how that blanking, piercing, and punching, right? It's just that the output that is desired changes, and therefore we name it a certain way, right? If the blank is desired, then we call it blanking. If the remaining portion after removing the blank, right, the remaining portion of the workpiece or the specimen is required, then it's called piercing, right? So you see shearing action taking place, as we have seen that shearing is the most dominant mode of, or it is the mode of deformation in blanking and piercing, right? That the punch tries to shear off this workpiece at the interface or the part where the die is actually having that loss, sorry, absence of material, right? You have a profile cut in the die, and the punch moves down. The punch also has the same profile. Just that there is some difference between the dimensions, right? This punch is kept a little smaller. The dimensions are less than the die. So if it's a diameter, if it's a circular punch, then you have the diameter difference. If it's square or prismatic, then you have it in terms of breadth and depth. So that is what is responsible for the shearing action, right? It presses, it tries to compress, but until it only compresses until the material fails, and it fails by shear, right? So that's what is happening, the shearing action. You see, if this is your final product or useful part, then that becomes scrap, right? And if the blank is a useful part, then we call it blanking. That's what I was talking about. If this is your useful part, then this becomes scrap, right? If this is a useful part, then we'll call it piercing or punching, right? The different views that we can have a look at. So piercing, you see, this is called piercing. If the useful part is your the top part that we will see, cross-sectional view of the same process. this summary, you can call it, of the video. Right. So from this sheet, we had this part, right? I mean, we had removed this part, and then the outer profile becomes a scrap, isn't it? The middle one, this one, and the outer profile. So that's functional, more like piercing, as was said in the video, right? So I hope that is clear. Right. Now, as for the forces, how do you calculate the forces? Because this is important for determining the press size. To select a proper press, right? As for the specifications, 10-ton press or 15 or 50 or right. How do you select? Based on the like these factors which you see. They depend on the shear strength of the metal, right? That's what you're cutting. So that and the stock thickness, right? The thickness of the sheet is also important. More the thickness, more will be the force required. And same goes for the shear strength, isn't it? More the strength offered, more is the strength of the material or the metal, more would be the force required to shear it, isn't it? It's that simple. And is the length of the cut edge. So more is the length, more would be the area of cross section, right? That we are shearing. So the area of shear would increase as thickness and length of cut increases. If you're looking at geometrical factors, if you're looking at material factors, then you have the shear strength. Increase of shear strength leads to increase of force that is required to shear it off. Right? It's that simple. It's a very simple formula, and that gives you the force. Strength, shear strength, as we measure it in Newton per meter square or Newton per mm square. Thickness is in, if let's say this is Newton per mm square, shear strength. That multiplied by your, should I write it? Newton per mm square, let's say, is your units for shear strength. Multiplied by, you have the thickness in mm, thickness of the sheet. Right? Let me draw that. If this is your 3D part, right? If this is your 3D part, let me draw that thickness as well. Right? If this is your sheet and you want to cut it like this, right? So if I cut it, I would see a cross section like this. Let me draw the cross section as well. The cross section will be somewhere, something. Okay. Right? So the cross section will be like this cross section, right? So to indicate the thickness, and this is your thickness, right? Here, right here, this is your thickness, and this is your length, L. So this L and that T are here. Basically the area that is being sheared off, right? Because of the force on the press, right? The shearing action from the press, that cutter would try to shear off this part down, right? While that part is resting on maybe some part of the die, right? This is resting, and then the punch would come and it would apply a pressure on this portion, the remaining white portion here, so that you can have shearing action. And when the shearing happens, the area that resists is this thickness times L, is the rectangular area. So that area is what is accounted here, right? So if that is the case, then that's what this is your geometrical factors, and this is your material factor. So yes, so as for thickness mm, and as for your length, it is again mm. So consistency of units if you maintain, this would cancel, and therefore you will get newtons as the force. How much force is required to select the press? You will need the force that is required to cut this particular sheet. These are the factors you have to take into account and get the force. Based on the force that is required, you have to select the press. Right? Simple calculations. I hope that is clear. Is that? Or any doubts? Okay. So you see, we had seen that metal forming is the reshaping of a section in a material by applying a combination of compressive and tensile stresses to induce deformation. That's the ultimate goal, to cause deformation, and therefore that would lead to shaping of a section in a material, right? Because it is usually some part of the sheet that we are trying to deform. It can be broadly categorized into bending and drawing, as we had discussed. Bending is straining sheet around a straight axis, right? As we have seen, probably yes, here is where we are trying to start bending here. That's what bending is, right? And drawing, forming of sheet into convex or concave shape, right? As you might have observed in forming that this circular kind of profile. Earlier the sheet was like this, right? I'm drawing a 3D version, and when the punch came, and it's a circular punch, right? And when it came down, you have this kind of shaping of the sheet metal because of this punch. And of course, there is a die at the bottom, needless to say. There is a die at the bottom, and because of this die, this sheet has been deformed like this because the punch moving down. So that's drawing, right? Forming of sheet into convex or concave shape. Here you can see a concave shape, isn't it? Concave shape. It could be even convex, right? Depends on how your punch is moving. If the punch is, let's say, of this shape, if the punch is of, let's say, this kind of shape, right? And you compress it against something like punch. I'm sorry, the die has the projection, and therefore you would have what do you call it? A convex shape as well. It's just reorienting or readjusting the die and punch. So basically, concave or convex shapes you can form. That's drawing. Bending is basically straightening the sheet around a straight axis. About an axis, you try to bend it. It's that simple, bending. This is your typical bending operation, and this is the terminology involved. So you have, as I said, straining sheet metal around straight axis to take a permanent bend, right? That's what is happening, permanent deformation, plastic deformation. If you bend it like this, what you have is a neutral axis or plane. You might have studied, right? You would have studied, right? Strength of materials 1 and 2, especially for 7. You have a plane or an axis that goes in between the total thickness that is not affected by either tension or compression, right? The outer profile, the outermost profile here you can see would be experiencing tension when that bend is executed or performed, right, using a bending machine. And the innermost layer, or yes, the innermost layer would experience compression, right? Especially here, more of a compression here than it is at some other points. So that uh, and there is a plane, there is a plane or axis, right? If you're looking at 2D, it's a plane. If you're looking at a 3D figure, then you have a plane, right? 2D, you're only talking about axis. So if W is the width of this sheet and T is the thickness, as we know, R is the radius of curvature, right, of that bend. This is very important. This is very critical and an important parameter that would decide how much bending stresses would induce. Because the smaller the R, the bigger is the stretch, or you can say the critical is the stretch. Smaller, greater R leads to less of stretching and permanent deformation, right? So those cracks, if they are to be avoided, have to be this R has to be taken into account. How much can you bend it depends on how small the R is or how big the R is. Depends on the value of the radius of curvature. Also depends on the timing of the bend, right? If it is suddenly bended or you are allowing it time to deform would also matter. And this is the bend axis, right? Needless to say, this is the axis about which this sheet is bending. That's why it's called the bend axis. And you see, metal on inside of neutral plane is compressed, as we know, as I explained in the last slide, while the metal on outside of neutral plane is stretched, and the neutral axis remains undeformed, right? Does not undergo either compression or tension. Both compression and tension elongation of the metal occur in bending, isn't it? So that's what we are trying to emphasize here. Bending is a metal working process by forming an angle or a curvature in the workpiece by including a plastic deformation to form the bend. Right? That's the comprehensive definition we can form. Forming an angle or a curvature in the workpiece through the help of this plastic deformation. It is done by forcing the forming die in the workpiece, and which is fixed in an opposing bottom die, right? The forming die, or you can call it the punch, right? That's a proper term to use if you want to avoid confusion. Bottom die and forming die. So they are referring forming die as they are referring punch as a forming die. So the downward stroke of the punch, here you see the punch gives the bend profile to be enforced in the workpiece. So it's the downward punch which is the productive, isn't it? So that's where changes are taking place. Some of the bending methods that can be performed in a stamping process include the following. We have what is called V bending, and another thing is called edge bending or metal flange. Right? So in V bending also you have two types: bottom pressing and air bend. Right? So basically the difference is bottom pressing, you would have some kind of a supporting surface when you're bending at the bottom of the workpiece or the worksheet. And whereas for air bending, it doesn't have, it bends in the air, and then at the end, you have to, it will be supported at the end. Supporting of the workpiece is actually at the end and not in between. So that's what's called air bend. Right? So you see, as for V bending, we can see this figure here. This is before bending, this is after bending. So you have the sheet taking the profile of the die and the punch because it is in between the die and the punch, so it has to take that profile. Performed on a press brake, V dies are simple and inexpensive. Right? That's V bending because you're making sure that the profile is actually V. Right? So as for bottom pressing, you can see that you have a smooth contour, right? Whereas for air bending, this basically is that punch will have to reorient, and it will not, the workpiece will not contact the die unless it reaches the bottom. So a proper support is not there in air bending. That's why it's called air bending, bends in the air, and therefore this is more likely to form cracks or failure of premature failure of the material, even though if the forces applied are within the limit, but because of stresses, right, that are not uh, within the capacity of this material, would lead to failure of this sheet metal, right? As for the types of sheet metal bending, V bending performed with a V-shaped die and edge bending performed with a wiping. So you see here edge bending for high production, pressure pad required. Dies are more complicated and cost. Sorry. So if this is the die at the bottom, you have the sheet with this brown color. The pressure pad here would kind of provide that holding force. It's also called a holder, blank holder, if you want to call it technically, blank holder or workpiece holder. So it tries to hold the workpiece while the punch is trying to bend the sheet. So this pressure pad is responsible for keeping it intact and making sure that it doesn't slide. Because as the punch would move down, causing this portion of the sheet to bend, it will cause some kind of a sliding action here. So if that friction is not ensured, then the sheet would just slip down, as simple. So there will be no permanent deformation, right? There will be no bending. How do you ensure that there is bending? You ensure that there is friction here. How do you ensure friction here? Through the help of a pressure pad. Apply pressure on the pressure pad ultimately applies it to the sheet. Sheet is resting against the die, therefore it contacts the die and therefore maintains some kind of friction force. And therefore it would be easier for us to bend the other portion, which is overhang of the sheet metal. So the force that is applied on the pressure pad is called FH, basically holder, right? Holder force. And V is the velocity of the punch, and therefore it exerts some force, right, based on that velocity, and therefore that is F. You see all these kind of bending are possible there. We have specific names for them. This is called straight flanging because the flange, this is called flange. The edge portion that is protruding is called the flange. And if it is straight, as we have seen in the last example, it's called straight flange. It could be even stretch flanging because it stretches if it is a circular, curved profile. As for shrink flanging, you have it outside, if you can observe, and therefore it would shrink at what do you call here at behind this sheet metal, isn't it? Here you're trying to stretch it because of that profile, outward profile. Hemming, this is one of the most commonly used method or technique performed for automotive components, especially, right? Or any other sheet metal which is to be bent over itself, right? So this would ensure that there's no sharp edges and also ensures that it can be what do you call hemmed to other sheet metal, isn't it? It is very much possible that we have another sheet in between. So this hemming would ensure that the sheet and this particular blue sheet is intact, right? They don't move relative to each other. So hemming is one of the most important techniques. Is one of the most important techniques when it comes to automotive industry, especially BIW, car door, etc., are hemmed, right? Hemmings performed. And then you have seaming as well. If you can observe that profile, seaming and curling. If you have to curl it to avoid sharp edges at the end, they usually curl it. If they cannot hem it, they will curl it. So the stretching that is happening during bending. If the bend radius is small related to stock thickness, the metal tends to stretch during bending, isn't it? As I was talking about in the previous slides, that if the bend radius is small, it will lead to stretching, more stretching during bending, right? Higher the curvature of the bend, lower is the stresses induced, and therefore lower is the stretch. Important to estimate amount of stretching, where final part length is equal to the specified dimension. So this is very important. You have to ensure that stretching is being accounted for. You have to account for all other external factors to come up with the stretch that would happen if we were to physically subject that sheet metal to that stretching. How do you estimate how much stretching will be done? So that we can decide upon the final dimension, right? If for example, this is the final dimension, let's say XYZ, how do I ensure that even after stretching, I would get this kind of dimensions? So for that, you have to account for the external factors such as the bed radius and the shear strength of the material sector. Problem to determine the length of neutral axis of the part before bending. Right. So before bending, we are going to look at the neutral axis. Bend allowance. How to calculate the bend allowance? It's given by 2 pi into a by 360 times r plus kba into t. Ba is your bend allowance. A is the bend angle we've already talked about. How much is it? 60, 70, 90 some cases. R is the bend radius. Is the bend angle. R is the bend radius. T is the stock thickness of the sheet metal. KBA is factor to estimate the stretching. So if R is less than 2T, right? This is actually the bend radius. We already know what is the bend radius, right? We have decided. So if R is your bend radius, and if R is less than 2 times the thickness of the sheet, then we'll take KBA as 0.33. If it is greater than or equal to 2T, then we'll take KBA as 0. Is it clear? As for you see the spring back, this is also another important issue when it comes to sheet metal forming, that you have the problem of spring back. What is a spring back? Increase the included angle of bend part relative to included angle of forming on tool after tool is removed. So once after performing the operation, either bending or forming, drawing, etc., once it moves, once that is removed, there is still some there is some strain. What do you call compensation of strain, or the strain? Some of this plastic deformation that was caused is not completely there. It tries to return back as well. Some part of the process will try to make it reverse, right? So if the increase in the included angle of bend, for example, if I had bent it to, let's say, this angle, right? I had bent, so let me put it like this. If I had bent like this, right, using a punch, initially the angle here was, let's say, 60 after forming, right? Once the sheet metal forming was done, it was intended, it was performed as this would remain as 60, and that is what is our specification. But because of spring back, this will try to move away. spring back property. It will actually lead to somewhat more angle, right? Both sides, here and here. So maybe let's say this increases to 65 degrees centigrade. I'm trying to exaggerate, and it is also possible, right? It's not an impossibility that you do have increase of as much as 5 degrees once the load is removed. So after the forming tool is removed, you have an increase in the included angle as what we are talking about. So this is not just, this is a simple demonstration of the problem. There are complicated problems as well. So how do you account fade spring back? How do we solve this problem? As for the reason for feedback, the bending pressure is removed. As I said, elastic energy remains in bent part. So that elastic energy is what tries to return back, causing it to recover partially towards its original shape. Right? The plastic deformation would be there, yes, but the elastic deformation, which was earlier, as you remember, when we were trying to bend a sheet, it goes from elastic zone to plastic zone, as we know. So the elastic zone recovery is possible, as we know. The recovery is possible for elastic zone, but for plastic zone, recovery is not possible. So once it starts from elastic zone, deforms a little, and then you go into plastic zone, and then it basically, when you remove the load, this sheet would now try to come, what do you call, change its angle to that. If it was 60 earlier, after executing the process, then it will try to increase because of the elastic energy that is there. Remember, the elastic energy is not dissipated yet. Plastic energy has been given, right, through plastic deformation, the sheet metal, but the elastic energy is still there, and therefore that will cause it to return. And that returning or change of angle or dimensions after removal of load is called spring back. Right? I hope that concept is clear of spring back. Is it clear? Okay. So you see, this is a problem of spring back illustrated in this figure. Spring back in bending shows itself as a decrease in bend angle and an increase in bend radius. Of course, right? Common sense. If the bend angle has increased, then the bend radius would also increase, right? Increase in bend radius. Yes. Increasing bend radius in the sense for smaller, for sharper corners, you have less of that radius, isn't it? You can see this sharp radius. You have a sharper radius here. So if there is an increase in bend radius, right? Maybe it is not 5 mm. Let's say it becomes 10, right? So it is